So for the first talk, we have Dr. Ram, and he obtained his MChem from Durham University, where he was working under Dr. Matthew Kitching on the synthesis of artificial molecular walkers. He then moved to the University of Liverpool for his PhD, where he worked with Professor Andy Cooper on high-throughput experimentation and chemistry automation. He then stayed on as a postdoc in the Cooper Group, where he's now working on the implementation of mobile robots for synthesis. So let's all welcome today Dr. Ram Vijayakrishnan. I shouldn't attempt to pronounce the surname, for his talk on autonomous mobile robots for exploratory synthetic chemistry.
So thank you very much for the organizers for giving me the opportunity to speak today. So I'll be speaking a little bit about some of the work that we've done very recently in the Cooper Group on mobile robots for organic synthesis. So we're going to start off with a small semantics exercise. So what's the difference between an automated lab and an autonomous lab? So in an automated lab, we would generally say that the humans are making most of the decisions. And so automated technology has been around for a very long time. For example, ChemSpeed platforms, Unchained labs, these sort of systems have been around for almost 25 years, 30 years at this point. Liquid handlers have been around for a long time. But at the end of the day, it's the humans who are making the key decisions in the experiments. At some fundamental level, it's all the platforms are doing is really taking away some of the very repetitive tasks. But they're not actually doing the higher level thinking that we would do in a sort of like a realistic chemistry experiment. And so the difference between an automated lab and an autonomous lab is where in an autonomous lab, we have the machines or the algorithms that actually make the decisions in the experiment. So they are the ones that are making the key experimental decisions. And so if you want to have an autonomous laboratory, you need a much higher level of trust and reliability inside your systems. For example, it's very easy to do things like biological liquid handling to some extent compared to something like synthetic organic chemistry, where you may be working with very dangerous synthetic reagents. You may be working with air-sensitive chemicals. But also from a practical point of view, given the diversity of chemistry that's out there, it's very difficult to sort of encode that decision making. So to actually enable the algorithms to have that decision making capability. For exploratory chemistry, this is actually very, very difficult because you often don't know what the data is that you're looking for in the first place without running the experiment. But then if you have to run the experiment to find out what the data is that you're looking for, what's the point of automation at that point? So we went about and tried to find a way to kind of address the solution. So if you're trying to do exploratory organic synthesis, you may, for example, have multiple steps inside your workflow. You might do an initial synthesis, and then from then on, you might do an LC to see how well your reaction is done. You may take some of those peaks on the LC, do MS to see what are the masses inside there, and but at this stage, you might do a sort of filter if your LC chromatograms are too messy, if you have too many peaks inside there, you might just stop at this point. You might not even take it forward. And from there, you might take it on for NMR. You'd go on to purification, structural identification, and then finally your definitive measurement at the very end of your workflow might be single crystal XRD, for example, to find something like an absolute configuration. But you can see in this sort of process that experiments have to pass through this sort of decision tree where researchers, they have to make like very qualitative judgments. And this is very easy for humans to do, but to encompass a wide range of chemistry and to teach algorithms how to do this, it's very, very difficult to actually do this in practice. And I think one of the things in particular is that if you especially if you want to have algorithms do some of these processes, it's very, for new techniques such as deep learning, machine learning, artificial neural networks, you need a lot of data. And compared to something like recommendation systems for social media, where social media posts are basically free, every single experimental point in an organic synthesis is very expensive. You may do 5 experiments at most, and your reaction time is 16 hours. So every single data point is very expensive, and you simply can't realistically build huge amounts of data sets to sort of feed these models at scale. Okay. But if you want to try and automate all of these things, you quickly end up with a logistical problem. And anyone who's worked in this sort of space understands that it's very difficult to sort of scale things up. And so many of the systems that are out there right now, they're very sort of integrated systems. So for example, you have your ChemSpeed, you have the LCMS that's sort of stapled on inside there, and they're very inflexible systems. They're very large. They're very technically complex systems, but you also end up with a very large scalability problem, because if you have one LCMS and one NMR stapled to one ChemSpeed platform, you can't just keep scaling this out infinitely. It's not even just it's not even just a financial cost. You need technicians to maintain the LCMS, maintain the NMR, and it becomes completely prohibitive to more than one sort of system. So we kind of came up with a solution for a solution to try and address this. We came up with a way of implementing mobile robots into a standard synthetic laboratory, and what these robots would do was shuttle samples to and from our synthesis platform to MS and NMR. So we use a standard LCMS that the only real modification is an automated tray loader, and we use a benchtop NMR. There are some reasons for this, particularly, but in this sort of characterization range that we have over here, most synthetic organic chemistry that a lot of people would do is easily characterized by these two methods. And what's great about this sort of implementation is that the instruments are sort of distributed anywhere inside the lab, and this allows for the equipment to not be monopolized by a synthesis platform, and it allows for researchers to work alongside the robots and to use the equipment when they're not specifically in use by the mobile robots. Okay, so I'll just show a video real quick of some of the system that we have right now. So this is our KUKA mobile robot that's transporting samples from our synthesis platform to an NMR. So you can see that we have these cubes at every single station. So this provides a 6-point reference for the robot to have a definitive location on where it is inside the map. So this is an LCMS over here. So the only real modification that we do at this point is just some 3D printed LCMS racks over here. And so we also have a photocatalysis station over here. So it's very easy to sort of like staple these bits of equipment onto the workflow. Okay. So we came up with a sort of generic synthesis decision analysis loop. So our ChemSpeed would synthesize things from whatever our ChemSpeed synthesized. We take our samples and we refactor them into separate analysis samples for LCMS and NMR. And so we use heuristics in the experiments that we did over here. We use heuristics to decide what experiments are going to be done next. So the decision is really based on expert chemists, and we find that this is a very data efficient way of actually trying to come up with sort of general rules for organic chemistry. And we'll go through some of the rules that in the next couple of slides. But this allows you to push very far ahead without having to do something like having to collect large amounts of training data. So once the algorithm goes through both the MS and the NMR data, in the experiments that we've shown over here, we need a hit from both an MS and an NMR to sort of get a characterization level that's sort of in parity with human researchers. And then this would inform the next step that we have inside the synthesis. Okay. So one of the workflows that we had in our paper was trying to have the discovery of metal organic architectures for host gas chemistry. So this entire workflow ran for 3 days fully autonomously. The only interventions that we had to do in those 3 days was really just to restock consumables like bios, some chemicals. That's kind of unavoidable, and in some sense is actually perhaps a bit safer not to have large amounts of chemicals inside a synthesis platform. So we started off with some common precursors that can be combinatorially combined to create these sort of architectures. So the robot initially does a screening stage where it does a permutation of these combinations, decides which ones are successful, and then replicates the successful ones. And then after it's done the replication, verifies that the replication is where the analytical data is in parity with the screening sample. It then takes the successful replicates onto host gas binding studies that we did later on. Okay. I'll go through some of the decision maker rationale that we have inside our workflow over here. And so generally we set some general rules for our experiment over here. For example, we set a bunch of criteria so that for example, the signals need to be shifted in comparison to the reagents. If you just have an NMR after the reaction and it's just a summation of the starting materials, there's probably no reaction happening. We set a rule that the sum of signals from the reagents has to be plus or minus 2. So this kind of so in general, we want like very clean chemistry that works quite well. And so regardless of what the reagents are, you can generally use number of peaks as sort of proxy for how clean your reaction is. And we also have an MS over here. So in one of the examples over here, you can see that largely the NMR is basically just for this experiment, for this combination of precursors over here, is largely just a summation of the starting materials. So in this case, the system rejects this to take forward for the replication stage. And there's also no MS hit as well. So in this case, we have nice shift from the reagents. It's a nice clean spectrum. So this is quite indicative of what might be a nice supramolecular architecture for us. But you can see that we don't have any hits on the MS. So this is rejected by the decision maker because it doesn't really have any of the MS hits that are inside there. So interestingly, we actually still don't really know what this compound is from our initial study. And we're still trying to sort of figure out what we've made in this case. Okay. So this is another case where the decision maker is being rejected, where you can have where you can see that yes, the samples have shifted. There are some new peaks inside there, but it's quite messy. So this is a case where we're not entirely sure where the decision maker isn't entirely sure that it's a very clean reaction and it's rejected. So even though we have an MS, it's rejected by our NMR criteria as well. Okay, and so finally, this is an example of one of the two of our permutations that were taken on to the replication stage. So you can see over here that the signals for the peaks are shifted from the initial starting materials, and we can see multiple hits on the MS from this combination. So this is a case where the decision maker would select this on for replication and then host guest binding studies later on. And so scaling out, so what the decision maker does, so what our system does is it replicates all of the initial thing, and it checks the analytical data for all our replications to make sure that the synthesis is actually verifiable. And so here the objective is different. So we look for, we want as minimal variations as possible from our initial pool. And so then we took some of these on for host guest binding studies. So this is largely just to measure how much we have changed. So we look for shifts inside our NMR of the bound versus unbound hosts. Okay. So one of the other examples that we did inside our paper that I won't really go into too much is a sort of more medchem inspired synthesis. So this sort of ran for 4 days. And again, like the main objective was to sort of create some common building blocks. We scaled these up rather than scaling out, and then we diversify them. So in this case, we did Sonogashira and click chemistry reaction. But again, it was for 4 days, and the only interventions really were restocking the chemicals. And so from then, one of the last examples that we did for this project was trying to show that we could integrate other pieces of equipment. So our chemistry platform, for example, doesn't have a photoreactor, but we could actually take this and we could actually just take a photoreactor and just staple it on somewhere inside the lab, and a robot would transport samples from the chemist bead to the photoreactor for analysis. And to sort of finish off, there's really, from what we've seen so far, there really isn't really a limit on the sort of scalability that we can do in terms of the system that we have right now. So you can imagine sometimes in the future where the mobile robots are just sitting around most of the time, you can have a fleet of mobile robots servicing multiple different chem suites, multiple different MS machines and NMRs, because really the synthesis is by far the biggest bottleneck, not the actual analysis and the robotics operations. So maybe this might be a vision for the future where you have an assembly line process. Okay. Just sort of finish up. So thanks for all the synthesis bots teams who worked on this project. Andy, especially for leading the project. The Leverhulme Research Center, especially for giving us sort of flexible funding that we needed to do this sort of project. So if anyone is interested in reading more about the work that we've done over here, it is published. So please feel free.